Assalamu alaikum. My name is Malik Najmul Siraj, and this is Data Communication Network course. But in today's class, we are going to talk about connection-oriented transport, which is TCP. We already talked about principle of reliable data transfer, connectionless transport, multiplexing and demultiplexing, and transport layer services. So in today's class, we are going to end this this chapter, which is transport layer. So TCP, you will find the RFC of TCP, detail of the TCP is mentioned in these RFCs. RFC 793, 1122, 1323, 2018, 2581. ठीक है, आपको you can find a lot of details of how the working of the TCP protocol and its other details in those RFCs. So in order to summarize all those things, let's talk about TCP. TCP is a point-to-point, one sender and one receiver. Okay? It's a process-to-process communication. It's a reliable in-order byte stream. It's a reliable data transfer protocol which deliver the data to the application as an in-ordered byte stream. It's a pipeline protocol. You can send multiple segments of the data. TCP congestion and flow control set the limit size. You can send the multiple segments of the TCP back to back, but there is a limit that is applied due to the window size and flow control. We will talk about those things later on in this course, in this lecture. It's a full duplex. It's a bidirectional data flow in same direction. Maximum segment size is we already talked about MTU, maximum transmission unit. Okay? Maximum segment size is the same as MTU, but it's on the transport layer. क्या आप एक segment के अंदर how much byte of data that you can send. It's a connection-oriented protocol. There's the handshaking between sender and receiver. We already discussed that thing. We've already seen that thing in many different places. It's a flow control. A sender won't overwhelm the receivers. Sender is sending a data to the receiver, but it will not blast the receiver. Okay? It is sending a data, but it will not overflow the receiver buffers. Okay? We will talk about this thing too in this lecture. So this is the header of the TCP. It has a source port, which is a 16-bit number. It has a destination port, which is again a 16-bit number. It has a sequence number and acknowledgement number. It is used, sender is sending which data. So receiver knows about the sequence number, and receiver is acknowledging the sender with the acknowledgement number. Okay, we will talk about that thing too, how this is used in TCP. It has different flags, urgent flags, generally not used, push flags, generally not used. It has an acknowledgement. Acknowledgement flag, once you are acknowledging, we already talked about that thing. And there are flags which is called reset, sin, and fin. These are the flags. We've already talked about those flags too. Once we are understanding about the TCP connection setup and tear down. So these flags are used in connection setup. You send a sin flag in order to make a connection with server or with any other system, and then reply to that. The other party send a sin plus ACK flag. Take a sin plus ACK flag, and then you send a sin flag. Take a reset flag is in order to terminate a connection, and fin flag is also used in order to terminate a connection, but it's a proper form to terminate a connection using a fin flag. Okay? Or the fin flag is used to terminate. If a party wants to terminate, it send a fin flag. ठीक है, हम लोग इसको भी जाके we'll talk about that thing. Same is in case of UDP. It is also having a checksum value. Receiver window size. Once we are talking about this thing, that sender won't blast the receiver. So how it won't blast the receiver? Using the receiver window size, number of the bytes receiver willing to accept. So sender is not sending bytes more than that. And these are the some optional field, and you have the application data field. So TCP sequence number. We already talked about this figure, so let's try to understand that figure with respect to TCP. Sequence number is byte stream number of byte in the segment data. ठीक है, हम लोग इसको और डिटेल में भी जाते हैं. acknowledgement number is the sequence number of the next byte expected from the other side. Let's say this is my window. Just mean these are the packets that are already sent, not yet acknowledged. These are the packets which are usable but they are not sent. These are packets which are not usable, and these are the packets which are already acknowledged. So once it is sending another packet, so it uses a sequence number which is of this packet, byte sequence of this packet. So it is sending a packet of this. So if receiver is acknowledging, so it is acknowledging with an acknowledgement number. Let's say it is acknowledgement this. So it is sending acknowledgement number of this byte. So but we will all look into those things more detail in upcoming slides. How the receiver handles out of the border, TCP does not. It's up to the implementer how it is, but it will tell you how you can reorder them in order to make an ordered data. So let's try to understand this thing. This is a host A and host B, which is establishing, which has already established a TCP connection. So host A, let's type C and send that C to host B, and host C is also sending back what it received. So let's talk, but we are going to look into those things with the sequence number, acknowledgement number, and the data. So it is sending data with a sequence number of, initially assuming this thing, the sequence number is 42, and it has an acknowledgement number of 79. Okay. So it means that this acknowledgement number tells that tells the B that host A is expecting a packet with a sequence number of 79. Okay. So once this host send our data, okay, so it is not sending a new data. What it received, it is just sending that data back. So the data remains the same, but once this host B is sending a data, it has a sequence number of 79. Okay, because this is the sequence number which this host is expecting, and it needs to acknowledge this sequence number. So this sequence number is 42, and and the data, the size of our data is 1 byte. So it is acknowledging that it is now expecting a sequence number of 43. So it is acknowledging, it is expecting a sequence number of 43. So once it received, it send another character, or it can be the same character. Now in that it has a sequence number of 43. So sequence number of 43 and acknowledgement number of 80. So this is a simple scenario, and this is how it increments sequence number and acknowledgement number and sequence number works together. So TCP round trip time. We know that TCP uses, it's a reliable data transfer protocol. So once a segment lost, so it needs to send that segment to the receiver. So sender needs to send that segment to the receiver. So how it find out the segment is lost? We know that there is a timeout field that we talked about once we are discussing about reliable data transfer. So it is using that timeout value, but how TCP estimate, how TCP find out the timeout value? Because the RTT, which is the round trip time, we know that it keeps on changing. Why? Because sometimes there is no packet in the network, so RTT is small. Once there are a lot of packets in the network, RTT is increasing. Once there's a congestion, it is increased more. So how to set the TCP timeout value? Longer than RTT, it should be longer than RTT. ठीक है, राउंड ट्रिप टाइम से बड़ा होना चाहिए, बिकॉज पैकेट गया है और पैकेट आया है, तो उसके बाद कुछ टाइम होना चाहिए जिसके बाद वो पैकेट इज नॉट रिसीव्ड, acknowledgement is not received, so it retransmit that packet with this assumption that packet get lost in the network. But if it is sending too many packets, और वी कैन से इफ देयर इज अ प्रीमेच्योर टाइम आउट, ठीक है, अभी टाइम आउट की एक्चुअल वैल्यू नहीं हुई थी और पैकेट आ रहा था, उसके बाद आया था, तो उससे अल्टीमेटली व्हाट हैपेंड इज मोर नेटवर्क बैंडविड्थ कैन बी मोर नेटवर्क बैंडविड्थ इज यूज्ड। तो हम लोग ये भी नहीं चाहते कि पैकेट की जो नेटवर्क की बैंडविड्थ है वो ज़्यादा यूज हो रही है। सो टू शॉर्ट प्रीमेच्योर टाइम आउट, अननेसेसरी ट्रांसमिशन, टू लॉन्ग स्लो रिएक्शन टू द सेगमेंट लॉक। सो हाउ टू एस्टिमेट? In order to estimate, we are going to introduce few terminologies. One is sample RTT, which is measured time from segment transmission until ACK received. ठीक है, ये आपने मेयर कर रहे हो जो कि आपका सैंपल जा रहा है और ACK रिसीव कर रही है, बट इट इज द RTT which is called as a sample RTT. and it varies a lot. ठीक है, it ignores, let's say we ignores retransmission. ठीक है, उसके ऊपर हम लोग इसको ignore कर रहे हैं. Sample RTT will vary, and we want an estimated RTT which is more smoother, which is the average of the several reset measurement, not just the sample RTT. So we are defining another terminology which is called an estimated RTT, which is the average weighted average of the sample RTT. So this is how we are computing the estimated RTT. Estimated RTT is 1 minus alpha. This is the word we are giving to the estimated RTT, previously value of the RTT जो कि estimate हुआ, and this is the current RTT of the sample which has a weight of alpha. Generally alpha is 0.1 to 5. It is very less, so we are giving a less weight to that. So let's need to understand this figure. In this figure, this blue graph shows that this is the sample RTT, and which varies a lot. So we want an estimated RTT that is much smoother. So this is the estimated RTT, which is the pink graph. So it is much smoother than the RTT. But we know that all the packets that are, if we set this estimated RTT as a timeout value, then all those packets that are above on this, above on this line, they are retransmitted. ठीक है, although उनकी आपके पास वो रिसीव हो रहा है पैकेट, उनका आपके पास यू आर रिसीविंग द एक्नॉलेजमेंट, इसकी एक्नॉलेजमेंट बहुत लेट आ रही है. बट अगर मैं इसको एज अ टाइम आउट सेट कर दूंगा तो क्या होगा, रिट्रांसमिशन बहुत ज़्यादा हो जाएंगे. ठीक है, रिट्रांसमिशन बहुत ज़्यादा हो जाएंगे. सो वी डोंट वांट कि रिट्रांसमिशन ज़्यादा हो, तो टाइम आउट इंटरवल इंट्रोड्यूस करते हैं. तो वी आर डिफाइनिंग अ मार्जिन which we call as a safety margin. ठीक है, estimated RTT के ऊपर we are on this top we are adding another thing which is called a safety margin, so that once there is a safety margin तो हम लोग क्या कर सकते हैं, we can save a lot और बहुत ज़्यादा retransmission को हम लोग control कर सकते हैं. So deviation RTT, which is called a safety margin, we compute a deviation RTT which is 1 times 1 minus beta into deviation RTT plus beta into sample RTT minus estimated RTT. Beta की typical value that is 0.25 होती है. ठीक है, so in this formula initially obviously इन सब formulas को जब आप compute करोगे तो initial value estimated RTT 0 है. तो यहाँ से आपके पास ये वैल्यू आया करेंगी और फिर नेक्स्ट आइट्रेशन हुआ करेगी, उस आइट्रेशन में ये एस्टिमेटेड RTT की आप पुरानी वैल्यू यूज़ किया करोगे. सो यहाँ से जब आप ये कंप्यूट कर रहे हो तो नाउ द टाइम आउट इंटरवल इन एक्चुअल TCP इज एस्टिमेटेड RTT प्लस 4 times of the deviation RTT, which is the safety margin, and that reduces the transmissions. So TCP is using a reliable data transfer protocol. TCP creates an RTT. ठीक है, we talked about how reliable data transfer protocol works. TCP creates an RTT on top of IP unreliable. It's a pipeline stream, cumulative ACK, a single retransmission timer. ठीक है, आपका single retransmission timer use हो रहा है. Retransmission triggered by timeout events and duplicate ACK. ठीक है, retransmission कब होती है, timeout event जब होता है या duplicate ACKs मिलती हैं. ठीक है, multiple duplicate ACK results into the retransmission, or if there is a timeout. This is the only two events that results into the retransmission. Let's initially consider a simplified condition where we ignore duplicate ACKs, ignore flow control and congestion control. ठीक है. So let's talk about that. So this is a host A and host B. Host A is sending our data to host B, and it is sending an 8 bytes of our data. So it has a sequence number of 92. So host B is acknowledging that data. Now you can see the acknowledgement number is 92. The next byte it is expecting, that is the acknowledgement number. अब next byte host B क्या expect कर रहा है? Sequence number 92 is the starting byte, and you need to add 8 more bytes. So it is 92, 93, 94, 95, 96, 97, 98, 99. So 99 bytes of data is already received to host B. So it is saying that now it is expecting a sequence number of 100. Okay? So it is sending that, but unfortunately that get lost in the network. So once it get lost in the network, there's a timeout event, and after the timeout, it retransmits that packet again. So it is a lost ACK scenario. There is another scenario which is a premature timeout. Premature timeout. So it send two segments. One is a segment which is a 92 sequence number, 8 byte of our data. Another which is a 100 sequence number and 200 bytes of our data. 20 बाइट्स ऑफ डेटा, ठीक है। सो 92 के बाद ये हो गया, और उसके बाद अगला सीक्वेंस नंबर उसका 100 आ गया, ठीक है, जो हम लोगों ने यहाँ पे एक्सपेक्ट करे थे। सो इसने ये दोनों भेजे हैं, बट जो एक्नॉलेजमेंट है वो लेट रिसीव हुई है, and there is a premature timeout which occur. So once there is a premature timeout occur की है, तो वो क्या करेगा, जो लोएस्ट सीक्वेंस नंबर का पैकेट है वो रीट्रांसमिट कर देगा, ठीक है। जब उसने वो लोएस्ट सीक्वेंस नंबर का पैकेट रीट्रांसमिट किया, आफ्टर सम टाइम इट रिसीव्ड अ पैकेट विद एक्नॉलेजमेंट नंबर 100 and 120, so it increased its pairs to 120, and then once it received 120 acknowledgement number, it says it has already received, or it is a delayed ACK that is due to the premature timeout. So that's why we don't want, if that is happening, premature timeout is happening a lot, that increase the retransmission. So TCP retransmission scenarios, TCP is using a cumulative ACK. We already talked about this thing. So once TCP is using a cumulative ACK, cumulative ACK is actually helpful in that. So host A sends a packet to host B. Same packets. Now let's assume that the acknowledgement number 100 packet with the acknowledgement number 100 get lost in the network. So this segment once get lost in the network, whereas the segment with the acknowledgement number 120 is received at the receiver. अभी उनका टाइम आउट नहीं अकर हुआ था, जब ये रिसीव हुआ तो it means that this host B already received all the packets before this acknowledgement, before this sequence number, ठीक है। इससे पहले वाले तमाम सीक्वेंस नंबर वाले पैकेट्स को रिसीव हो गए, तभी उसने ये एक्नॉलेज किया, वरना ये उसी सीक्वेंस नंबर को दोबारा एक्नॉलेजमेंट कर रहा होता। इस बात को मैं ज़रा आगे जाके डिटेल में एक्सप्लेन करता हूँ कि कैसे वो दोबारा उसी सीक्वेंस नंबर के पैकेट को दोबारा एक्नॉलेज कर रहा होता, दैट रिजल्ट्स इन द फास्ट retransmission. So even at the receiver, arrival of in-order segments with the expected sequence number, अगर in-order segments आ रहे हैं expected sequence number, all that up to the expected sequence number already act. ये अगर event occur करता है और वहाँ तक data already act होता है, तो delayed ACK यूज़ करता है TCP and waits up to the 500 millisecond for the next segment. If no segment, sends the ACK, ठीक है। 500 millisecond तक वो wait करेगा और उसके बाद वो काम करेगा। Arrival of in-ordered segment with expected sequence number, ठीक है। in-ordered segment है लेकिन expected sequence number है। One other segment has ACK pending, लेकिन एक किसी segment की ACK pending है। Immediately send a single cumulative ACK, ठीक है। आपने single cumulative ACK भेजी है जिससे आपने वो तमाम in-order को आपने कह दिया कि it is received. Arrival of out of order segments higher than expected sequence number. अब मेरे पास segments आए हैं, out of order आए हैं, लेकिन मेरे पास expected sequence number से बड़े आए हैं। जब वो बड़े आए हैं एक्सपेक्टेड सीक्वेंस नंबर से, तो आपने इमीडिएटली डुप्लीकेट ACKs ट्रांसमिट किए हैं, दैट इज कॉल्ड अ फास्ट रिट्रांसमिशन, ठीक है। इस सिनेरियो को जो मैं प्रीवियसली जिक्र कर रहा था, इसको हम आगे जाके मजीद अच्छे फॉर्म में देखेंगे। नाउ आपने डुप्लीकेट्स ACK सेंड किए हैं, जिसका मतलब ये है कि सेंटर को ये पता चल जाए कि मुझे इससे हायर एक्सपेक्टेड सीक्वेंस नंबर के पैकेट्स तो मिल गए, लेकिन मुझे ये वाला पैकेट अभी नहीं मिला। सो यू नीड टू सेंड द पैकेट विद दिस सीक्वेंस नंबर, ताकि वो फास्ट रिट्रांसमिशन हो सके, इंस्टेड ऑफ सेंडर वेट्स फॉर द टाइम आउट एंड सेंड दैट पैकेट। Arrival of segments that partially or completely fills the gap, immediately send the ACK provided by the segment starts at the lower end of the gap. So TCP uses fast retransmission, which is if sender receives 3 ACKs for the same data, triple duplicate ACK, ठीक है। सेम डेटा के 3 ACKs उसको मिली है, रीसेंड द अनएक्ट सेगमेंट विद द स्मॉलेस्ट सीक्वेंस नंबर, जो भी स्मॉलेस्ट सीक्वेंस नंबर का पैकेट था उसको वो सेंड कर देगा, ठीक है। टाइम आउट पीरियड ऑफन रिलेटिव लॉन्ग, ये थोड़ी सी हिस्ट्री है जो वी ऑलरेडी टॉक्ड अबाउट दैट। सो दिस इज व्हाट इज अ फास्ट रिट्रांसमिट। सो सेंडर विच इज A इज सेंडिंग अ डेटा टू B, इट सेंड 1 2 3 4 5 packets. So let's assume that this packet get lost in the network, this segment get lost in the network, which has a sequence number of 100. But it received all those packets. So this is the packet that it is expecting to receive, and it receives a packet which is the higher sequence number. So instead of sending an acknowledgement of higher sequence number, once it is sending a packet, so इसने इसकी acknowledgement 100 send की, it is expecting a sequence number 100. जब इसको ये पैकेट रिसीव हुआ, इसने फिर acknowledgement 100 send की, फिर acknowledgement, फिर now it receive a triple duplicate ACKs. So once it receives a triple duplicate ACK, it immediately retransmits the packet with the sequence number 100 instead of waiting for a timeout. So it's a fast retransmission, ठीक है। फास्ट रिट्रांसमिट, फास्टली उसने रिट्रांसमिट कर दिया इंस्टेड ऑफ वेटिंग फॉर अ टाइमआउट इवेंट टू occur. flow control. So TCP flow control, flow control क्या है? Receiver controls sender, so sender won't overflow the receiver buffer by retransmitting too much too fast. ठीक है, रिसीवर के पास कुछ, अगर मैं रिसीवर देखूं तो रिसीवर का मेरे पास ये पैकेट रिसीव हो रहा है उसके पास, ठीक है, उसके पास आईपी, आपके पास नीचे इंटरफेस दिया हुआ फिजिकल इंटरफेस, ठीक है, उसके पास बफर स्पेस अवेलेबल है, देन ऊपर ये एप्लीकेशन दिखाई गई है, ठीक है। अब मेरे पास जो बफर स्पेस है दैट इज़ अ लिमिटेड बफर स्पेस, ठीक है, दैट इज़ अ लिमिटेड बफर स्पेस। ऐसा नहीं है कि इनफाइनाइट बफर स्पेस रिसीवर के पास पड़ी हुई है। अगर रिसीवर के पास पैकेट्स आते हैं जो कि नंबर ऑफ बाइट्स उनकी उस बफर स्पेस ज़्यादा होती है, तो वो क्या करेगा, रिसीवर उनको स्टोर नहीं कर सकेगा, रिसीवर स्टोर नहीं कर सकेगा और पैकेट लॉस हो जाएंगे। तो रिसीवर सेंडर को कम्युनिकेट कर देता है कि आप मुझे पैकेट भेज सकते हैं, बैक टू बैक जितने मर्जी पैकेट भेजें, लेकिन मेरे पास इतनी बफर स्पेस अवेलेबल है। सो इफ यू आर सेंडिंग पैकेट्स मोर देन दैट बफर स्पेस, आई कैन नॉट होल्ड दैट पैकेट, सो प्लीज डू नॉट सेंड पैकेट मोर देन दैट बफर स्पेस. So in this way it is receiver is controlling the flow of the traffic between sender and receiver. So this is called a flow control. So this is the buffer space, total buffer space, and this is the data which is already buffered, data which is already stored in this buffer space, and this is the space which is already available. So sender is telling the receiver that you can send our data to me, but that data should not be greater than this window size, ठीक है, free buffer space which is a window size. Receiver reprises the free buffer space by including the receiver window size value in the TCP header of receiver sender segment. Receiver buffer size set the socket option, by default it is 4096, ठीक है, by default value इसकी होती है. Many operating system auto adjust buffer, वो आपको adjust because sender limit the amount of unacked in-flight data, guarantee the receiver buffer will not overflow. अब sender data भेजेगा, लेकिन वो डेटा जो भेजेगा बैक टू बैक वो इस बफर स्पेस से ज़्यादा बफर का डेटा नहीं होगा, बिकॉज दिस इज ऑलरेडी कम्युनिकेटेड बाय द रिसीवर टू अ सेंडर कि आपने से ज़्यादा डेटा मुझे नहीं भेजना. So this is how what is flow control. Connection management, we already talked about connection management a lot of different times once we are talking about different applications. So let's again formally talk about before exchanging data, sender and receiver handshake. It's a connection oriented protocol, so they do handshake. How they do agree? They agree to establish a connection, each knowing others. Agree on connection parameters, ठीक है, client server ने different parameters को agree कर लिया. For that you need to open a socket, और socket आपके पास, आप उसको host ने बता रहे होंगे, port number बता रहे होंगे, और ये port number एक source destination का अपने port number है जिसको आप accept कर रहे होंगे, बना रहे होंगे. So TCP do a three-way handshake, performs a three-way handshake. So it's a client, it's a server. So client send a packet, client is in with a SYN bit is equal to 1, and let's say sequence number is X. Choose the initial sequence number X and send a TCP SYN segment, ठीक है, आपने SYN bit 1 करके भेज दिया. जब सेंडर होगा, जो रिसीवर होगा, रिसीवर क्या कर रहा है, रिसीवर अप्लाई कर रहा है, चूज द इनिशियल सीक्वेंस नंबर, वो अपना एक इनिशियल सीक्वेंस नंबर चूज कर रहा है, वाई वैल्यू, ठीक है, सेंड TCP SYN ACK मैसेज एंड ACKing SYN, ठीक है. उसने क्या किया, उसने इस SYN को उसने ACK किया, इस SYN को उसने ACK किया, एक्नॉलेजमेंट नंबर उसका X+1 कर दिया, उसने एक्नॉलेजमेंट फ्लैग को 1 कर दिया, और इसने SYN बिट को भी 1 कर दिया, और सीक्वेंस नंबर Y कर दिया, ठीक है. ये इनिशियली दोनों ने रैंडमली चूजन सीक्वेंस नंबर होते हैं, ठीक है. सेंडर भी अपना रैंडमली चूज करता है, रिसीवर भी रैंडमली चूज करता है, और उसके बाद मूव ऐसे करते हैं. अब ये रैंडमली अगली दफ़ा चूज नहीं कर सकेगा. सो यहाँ पे वो सेट SYN कर दिया था. अब इस पॉइंट के ऊपर जब उसको ये मिला है तो रिसीवर इंडिकेट्स दैट द कनेक्शन इज एस्टैब्लिश्ड. रिसीवर के पास कनेक्शन इस पॉइंट के ऊपर एस्टैब्लिश कर दिया. रिसीवर ने क्या किया है, इसको ACK किया है. अब ACK करते वक्त को क्या करेगा, सीक्वेंस नंबर Y+1 यूज़ करेगा, और एक्नॉलेजमेंट बिट 1 यूज़ कर रहा है. सो इट इज़ टेलिंग कि नाउ इट इज़ गोइंग टू एक्सेप्ट द कनेक्शन. इसने जब रिसीव किया और इसने कहा कि कनेक्शन एस्टैब्लिश्ड हो गया. दिस इज़ हाउ द कनेक्शन इज एस्टैब्लिश्ड बिटवीन सेंडर एंड रिसीवर. TCP closing a connection. अब connection को close कैसे करते हैं? Client server each closes their side of the connection. Send a TCP segment with the fin bit 1. So it is sending a TCP segment having a fin bit is equal to 1. Respond to receiver fin bit with ACK. ठीक है, so on receiving the fin ACK can be combined simultaneously. Fin exchange can be handled. So this is how the connection is terminated. So the connection is established between client and server, TCP connection. So if this client wants to close that connection, it send a segment with a fin bit equal to 1 and a sequence number. This is again a randomly chosen sequence number. So it send a packet with the acknowledgement bit equal to 1, okay, and acknowledgement number equal to x plus 1, okay. Now once this is received at the client, so now client cannot send a data on this segment on this connection, whereas the server can send, this party can send a data on this connection, because now this party closes the connection and it is in a wait state that server should close the connection. So server भी again fin bit को send करेगा और ये उसको fin bit को acknowledge करेगा, तो उसकी वजह से दोनों का connection close हो जाएगा. अगर वो नहीं करेगा तो वो data उसके तरफ में. So at this time server can send a data. So once it send a fin bit equal to 1 with a sequence number this, so now at that point the connection is closed on the server and on the receiver side. So both the parties need to close the connection. ये ऐसे नहीं होगा कि once a party single party can closes the connection. Both the party needs to agree to close the connection with the, and so both the party need to send a fin bit equal to 1. So now we are going to talk about principle of congestion control, which is article 3.6 of your book. So in TCP, congestion can occur. In a network, congestion can occur. So we know that TCP uses a congestion control mechanism. So how it is using a congestion control in a network? Congestion informally, too many sources sending too much data too fast for network to handle. ठीक है, बहुत सारे सेगमेंट भेज रहे हैं डेटा और इनफॉर्मली बहुत ज़्यादा डेटा भेज रहे हैं, जिसकी वजह से कंजेशन अगर करे. डिफरेंट फ्रॉम फ्लो कंट्रोल. फ्लो कंट्रोल और ये कंजेशन कंट्रोल इज डिफरेंट. फ्लो कंट्रोल में रिसीवर अपने बारे में बता रहा है सेंडर को, भाई कि नेटवर्क में पैकेट हो या ना पैकेट हो, आपने मुझे यू कैन नॉट सेंड अ डेटा विच इज ग्रेटर देन दीज नंबर ऑफ बाइट्स. Whereas in case of congestion control is totally different than that. It is saying that in a normal circumstances there is no congestion, you can send a lot of data, but in case when there are too many packets that are moving in a network, so congestion can occur. So once congestion can occur, you need to control, you need to limit, you need to reduce the amount of data that you are sending. So different from flow control, manifesto lost packets or and long delays. Once there is a congestion occur, so what happened is packet get lost. Okay, packet get lost and retransmission is going to increase in the network. And other is long delays. ठीक है, अगर congestion occur होने के करीब है तो delays increase हो रहे होंगे. More packets router की input के ऊपर wait queues के ऊपर wait कर रहे होंगे, that increases the router queuing delay. So let's talk about causes and cost of congestion, and we discuss multiple different scenarios. In this scenario, it shows that you have two hosts, two senders that are sending, and there are two receivers that are receiving. One router that is a router, and output link capacities are, and there's no retransmission. So once there is no retransmission, so both these hosts equally share this link, which is R. So lambda in, which is the throughput of host A, should be R by 2. In दोनों के host A and host B equally shares the channel R, so their throughput is R by 2 of each host. So if lambda in is increasing, lambda out is increasing. ठीक है, till the time which is R by 2. ठीक है, but once they both approaching R by 2, तो congestion occur at the length, so it increases the relay to infinity. ठीक है, so in this scenario we are assuming that the router has infinite buffers. ठीक है, there is no issue in the router buffer, so these hosts are sending data and it has infinite buffer to store that data. So there is no issue caused by the packet loss in the because of the router. So there's only thing that is matter here is the link capacity. So link capacity cannot be increased by each of the respective host A and B. So there's another scenario which has finite buffers. Now assume that this router has finite buffers. So once this has finite buffers, so ultimately once and this is lambda n, which is the original data which is sending, which is this host is sending, and since it has limited buffer, so a time will come when there's no buffer space available at the router. Once there's no buffer space available at the router, so packet get lost. Once packet get lost, they are retransmitted. So lambda in dash is the original data plus retransmitted data. Okay? So it is retransmitted data. So idle scenario, perfect knowledge sender only sends when the router buffer is available. Okay, so router somehow sender knows that there is a space available at the router buffer, and it is sending data only when there is space available at the router buffer. So in that scenario, this is the packet which is transmitted, so it creates a copy. So why? Because if it requires retransmission, then it will retransmit that copy of a data. So that data is received at the receiver with this thing that there is no loss because of router buffers. So there is another scenario. In this case, router lambda n is equal to lambda 2, and it is increasing. Lambda out is increasing as lambda n is increasing till the r by 2, because they both share equal throughput. So we know that packet loss occurs. So packet can be lost or dropped at the router due to full buffer. So once there is no space available, so packet get lost. So this is a packet which is sending, and at the router there is no buffer space available. So this packet get lost. Once this packet get lost, there is a timeout event that occur. So once there is a timeout event that occur, then this copy is retransmitted. And assume that at that point there is a free buffer space available, so it get passed to the router and receiver the destination. And there's a third scenario which is delayed or premature timeout. Okay, premature timeout. Okay, so now in that premature timeout, it send a copy, it send data, it creates a copy of a segment, buffer space available, but there are a lot of packets, so a timeout occur. At the once timeout occur, it resend the transmit packet. So at that point, more data is flow over the link, so capacity is reduced. So in this scenario, in this particular scenario, lambda n dash is greater than lambda n. So in this scenario, this is the lambda n dash, which it says that this lambda n dash never equal to r by 2 because of the retransmission. Okay, so when sending r by 2, some packets are retransmitted, including duplicate that delivered. So realistic packet get lost, dropped at the router due to full buffers. Sender times out prematurely, sending 2 copies, both of which are delivered. Cost of congestion is more work on transmission of the good throughput. You need to पैकेट गेट लॉस्ट तो आपको रिट्रांसमिट करना पड़ेगा, ठीक है, अननीडेड रिट्रांसमिशन हो रही है, ठीक है. Now in this scenario, let's assume that these are the hosts, and these hosts are sharing these 4 senders, multi-hop network and timeout and retransmit. So this host is also sending a data, and that is passed to this router. So once this read lambda in and lambda n dash increases, so what is the consequences of that? The consequences is there is no space available of free packet. So ultimately that results into the loss of the packet of blue packet at the upper queue get dropped, and blue throughput goes to 0. So once it is increasing, the blue throughput ultimately goes to 0, ठीक है, because packet loss का effect इस user के ऊपर भी आ रहा है. अगर इस congestion हो रही है तो congestion खाली इसको affect नहीं कर रही, that is also affecting the other users in the network. So overall the performance of the network deteriorates a lot. So there are 2 approaches to handle congestion. The TCP uses end-to-end congestion methodology. There is no explicit feedback from the network nodes, ठीक है. Sender identifies the packet lost by timeout or congestion inferred from the end system observed loss, approach taken by the TCP. And there is another methodology which is called a network assisted congestion. Router provides feedback to the end system. So router is providing feedback to the end system that now there's a congestion occur on this router. If you are sending a data to me, then reduce the throttle. TCP, this is what is the principle of congestion, or congestion कैसे occur कर रही होती है. So what is the methodology that TCP adopted in order to overcome the congestion? So TCP adopted TCP Congestion Control. Adaptive increase and multiple rate of decrease. Approach is sender increase the transmission rate, which is the window size. ठीक है, window size of a window size, sender is increasing the window size. So these are the packets that sender can send back to back. Probing for the usable bandwidth until loss occur. ठीक है, बैक टू बैक पैकेट भेज रहा है और उसको एडिटिव इंक्रीज कर रहा है. वंस एक्नॉलेजमेंट कम, सो इट इंक्रीजेज द कंजेशन विंडो बाय मैक्सिमम सेगमेंट साइज. सो एक सेगमेंट साइज इंक्रीज करता जा रहा है. सो वंस फर्स्ट सेगमेंट इज सेंड उसकी एक्नॉलेजमेंट मिली है, तो नेक्स्ट टाइम 2 सेगमेंट बैक टू बैक सेंड कर रहा है. उनकी दोनों की एक्नॉलेजमेंट मिली है, तो फिर 3 सेगमेंट है, 4 एंड सो ऑन. Multiplicative decrease. Once there is a loss occur, once there is a loss occur, so then it decreases the congestion window to half. So this is type of a sawtooth waveform. So it increases the congestion window size. Once there is a loss occur, let's assume at this point, so it reduces the congestion window to half, and then again additive increase. At this point, loss occur, so it reduces the congestion window to half, and then again increases, and so on. So this is type of a sawtooth behavior. So TCP congestion control is sender limits the transmission. कैसे है limit sender की transmission rate? Congestion window. This is my congestion window. Okay, this is my congestion window. These are the packets that are already sent. These are the packets that उसने उसको send करने हैं. अभी तक ये सेंड नहीं किए. ये पैकेट्स हैं जिनकी एक्नॉलेजमेंट नहीं आई. ये पैकेट्स हैं जो कि कंजेशन विंडो के बाहर हैं. ये पैकेट्स हैं जो कंजेशन विंडो के बाहर हैं, जो भी यूज़ नहीं कर सकता. एंड दीज आर द पैकेट्स जो कि वो बैक टू बैक कर सकता है, सेंड कर सकता है. सो कंजेशन विंडो शुड बी लेस दैन लास्ट बाइट सेंड. दिस इज द लास्ट बाइट एक्ट एंड लास्ट बाइट सेंड. ठीक है, ये हमेशा कंजेशन विंडो के अंदर होना चाहिए. अगर ये यहाँ से यहाँ तक आ जाएगा तो ये इससे इंक्रीज और नहीं करेगा. ठीक है, ये हमेशा कंजेशन विंडो के. कंजेशन विंडो इज डायनामिक फंक्शन ऑफ रिसीव्ड नेटवर्क कंजेशन. TCP sending rate roughly send congestion window bytes wait RTT for the acknowledgement. ठीक है, आपने कंजेशन विंडो का पैकेट भेजें और आपने RTT तक का वेट किया, एंड देन सेंड मोर बाइट. तो रेट आप निकाल सकते हैं कंजेशन विंडो डिवाइड बाय RTT, बिकॉज आपने कंजेशन विंडो तक के पैकेट्स भेज दिए हैं और आपने RTT टाइम वेट कर रही है. सो आप रेट निकाल सकते हैं इन टर्म ऑफ बाइट्स पर सेकेंड के TCP में क्या यूज़ हो रहा है. So TCP uses a slow start. So first send a 1 segment, it get ACK, now send 2 segment. Once they get ACK, send more segment. So it send 1 segment ACK, it send another segment, two segment. This segment get ACK, it send 2 segments. So once 2 segment get ACK, it send 4 segment, and then it is increasing window. Initially congestion window to 1 maximum segment side. Double congestion window every RTT. Every RTT it increases. This is the RTT. Every RTT the congestion window increases. Double. Initial rate is slow but ramped up exponentially. Initially वो slow चल रहा है, लेकिन वो ऐसा ऐसा increase हो जाएगा. So TCP uses 2 type of methodology. Loss जब occur कर रहा है तो 2 तरह की methodology use कर रहा है TCP. एक है called TCP Reno, which says that duplicate ACK indicates a network capable of delivering some segments. ठीक है, but this is where it differentiates between TCP Reno and TCP Tahoe. Congestion window is cut in half window, then grows. ठीक है, TCP Tahoe, once there is a loss occur, it decreases the congestion window to the half. Whereas in case of TCP Tahoe, once loss occur, congestion window timeout occur, the congestion window is set to 1. So this is the difference between congestion window between TCP Tahoe and TCP Reno. So initially there is an exponential increase. ठीक है, at this point after the threshold linear increase हो रहा है. And once at this point loss occur. Once loss occur in case of TCP Tahoe, congestion window set to 1. ठीक है, where in case of TCP Reno, congestion window set to half of the threshold. Last maximum value is 12, so it decreases to 6. Okay, and then ramps up, Whereas in case of TCP tau, this is the exponential increase till the threshold values and then additive increase. So average throughput, if you want to find out the average throughput, this is actually becomes a sawtooth waveform or window size W by 2 to W आपका हो रहा होता है. And we are not going in detail how we are going to find out that formula, but in case of a TCP, you can measure the throughput by 3 by 4 into W by RTT, and this is byte per second, which tells you the throughput of TCP. TCP fairness. TCP fairness is if there are if there are two connections, the both two connections share equally the bottleneck, all the links. So if there are two connections and the link is R, so if they both equally share the link and each get its share, which is R by K. So if K TCP session shares the same bottleneck link, the bandwidth R each should have the average rate R by K. Fairness in UDP. Multimedia apps often use TCP. Multimedia apps often do not use TCP, do not want a rate throttled by the congestion window. Instead, use the UDP. We already talked about this thing, multimedia, because multimedia app आपका UDP use कर रहा है, and these are the reasons that we already talked about why they are using. Fairness, which is parallel TCP. Applications can open multiple parallel connection between two hosts, web browser, multiple connection, and तो each connection को equal share मिल रहा होगा. So this is the summary, and this pretty much ends your chapter number 3, which is on the transport layer.